Okay, with these friends, after looking at how we can represent the complex number on the Venn diagram, we are going to look at another aspect, that's the modulus of a complex number. In short, the modulus of a complex number is its length. How is the complex number far? How far is it from the origin? So if we are given a complex number z, we looked at the previous video, we saw how we can represent it on a complex on the Venn diagram, that's the real and the imaginary. And with this, we shall represent the real part A and the imaginary part B on the y-axis. And now we are looking for the length from the origin to where the complex numbers ended. That length is what we call the modulus. We represent it with the magnitude of z. And if you look at this, this is a right-angled triangle with 90 degrees at this point, and the length, since from 0 to this point here, we are saying it's coordinate A, then it means that the length from 0 to that point is A. And also, since from here up to the upper part where we plotted the imaginary part is bar, then it means that the length from the real axis to where the complex number is B. And therefore, we have a right-angled triangle of this nature. We have 90 degrees there. This side is A, this side is B, and this side is what we are referring to as the modulus of Z. And now, if we are to apply the Integral Theorem, which says the longest side squared is equal to the sum of the two shorter sides squared, we shall have the modulus of Z squared equals to the shorter side squared, the sum we add, plus the other side squared. And from here we make the modulus of z, the subject, and it's the square root. That's the square, taking the square root on both sides, the square root of a squared plus b squared. This means that whenever you have a complex number, 1, you have to compare it with the standard, the general standard, or the standard complex number, which is a. The standard one that we base on has a plus in the middle, so you compare it with this to identify your real part and the imaginary part. And now to get the modulus, we square the real part and we also square the imaginary part and take the square root. Say for example, if we are given this complex number here, I'm going to compare this complex number 3 minus 2i with a plus ib. The real part is a 3. It means that my a is a 3. Then the imaginary part, here the imaginary part is positive b. Now here I have negative. It means that this b here that I have to consider is the one that was a negative, to make it look like 3 plus negative 2i in this form, because the standard one has a plus in the middle. It means that this negative was a value of negative of this b here. So if I'm to get the modulus of the complex number w, I'll have my real part, I square it, plus the imaginary part, which is negative 2, but I also square. Please, wherever it is a negative, put the brackets, because some of you end up messing up by forgetting the negative that is also going to be squared. So when we square 3, you get 9, plus when you square negative 2, you get 4, and then when you add 9 plus 4, you get 13. So the root of 13 is the modulus of this complex number here, or is the length of the complex number w from the origin. Because it is length, we put units. Yeah, some of you, I know you may need to press the calculator because you don't want to see the root sign in your answer. It's fine, only that if it is also giving you something that is simple like root 13, it's better you leave it there. Now we are looking at the modulus and we want to see some of the properties of the modulus. There are two properties, and the first property says if we are taking the modulus of a product of two complex numbers, it is the same as taking the product of the modulus of each of the complex numbers, meaning we get the modulus of the first complex number different, we get the modulus of the second one, and then we multiply them. Then if you're dividing two complex numbers and you want to get the modulus of the quotient that you're going to get, it is the same as getting the modulus of the first upper complex number, and then you divide it with the modulus of the second one. Here there is some number that I want you to try out, and I'm going to add a little bit more because here there are only two Romans. I'd like you to also verify this basing on these two complex numbers. If you have Z1 as this and Z2 as this, you're going to obtain for me Z1, the modulus of Z1. You also get the modulus of Z2. Then you get the modulus of Z1 times Z2, and you see whether these properties are correct. That is Roman number 3 of the exercise that I want you people to try out is find modulus Z1 and modulus Z2 and verify the above properties. So for this lesson we are ending here, and in the next video we shall start by looking at the argument of a complex number. Thank you.